What's going on, you guys, and welcome back to MIE 270. Today is tutorial number 2, and we're going to be continuing off of where we left off last time on failure and fracture part 2. Let's begin with problem 1. So problem 1 says a fatigue test was conducted in which the mean stress was 50 megapascals and the stress amplitude was 225 megapascals. A says compute the maximum and minimum stress levels, B compute the stress ratio, and C compute the magnitude of the stress range. So let's start with part A. So part A asks us to calculate the maximum and minimum stress values, but the problem only gives us our mean stress and our stress amplitude. So let's write down our two equations and figure out if there's anything we can do through manipulation and solve for our unknowns. So our stress amplitude is equal to our maximum stress minus our minimum stress divided by 2. And our problem tells us that our stress amplitude is equal to 225 megapascals. Now we can write down our mean stress equation. So our mean stress equation is equal to our maximum stress plus our minimum stress divided by 2. And the problem says that that's equal to 50 megapascals. Let's further refine these equations and simplify. So we can say that our maximum stress is equal to 450 megapascals plus our minimum stress. And our second equation could be simplified to our maximum stress is equal to 100 megapascals minus our minimum stress. So if we take a step back and look what we just did, we've just developed a system of equations. We have two equations and two corresponding unknowns, being our maximum and minimum stress. So this will be equation 1, this will be equation 2, and our unknowns will be our maximum and minimum stresses in both. So if we couple these two equations together or set them equal to each other, we can solve for a minimum stress and then perform backward substitution and solve for our maximum stress. So that's what we're going to do. So let's say that equation 1 is equal to equation 2 and set them equal. So 450 megapascals plus our minimum stress is equal to 100 megapascals minus our minimum stress. So after isolating for our minimum stress, you're going to get a value of our minimum stress is equal to negative 175 megapascals. Now, let's substitute that value back into one of our previous equations and calculate our maximum. So let's say that our maximum stress is equal to 450 megapascals plus a negative 175 megapascals, and that's going to yield a value for our maximum stress as 275 megapascals. So when you read a problem, figure out what's given to you, write down the equations that you have, and then try and manipulate them to solve for what your unknown is. So that's what we did here. We had two equations, two unknowns, and we're able to solve for our maximum and minimum stress values. Let's move on to part B. So part B wants us to calculate the stress ratio. So now that we've calculated our maximum and minimum stress values, this is trivial. We can say that our stress ratio is equal to our minimum stress divided by our maximum stress, which is just the values that we previously calculated. So we can say that negative 175 megapascals divided by 275 megapascals is going to give us a value of negative 0.67 as our ratio. So we can say our stress ratio is equal to negative 0.67. And part C says compute the value or the magnitude of the stress range. So the stress range, or designated by sigma r, is just our maximum stress minus our minimum stress, which is equal to 275 megapascals minus a negative 175 megapascals, and that's going to be equal to 450 megapascals. So we can say that our stress range is equal to 450 megapascals. So that's the conclusion to problem 1. Let's move on to problem 2. Problem 2 says the fatigue data for a brass alloy was collected and graphed into an SN plot as shown below. A says determine the fatigue strength at 4 times 10 to the 6 cycles and B says determine the fatigue life for 120 megapascals. So before we go in to solve the problem, let's make sure that we all know how to read a log-log plot properly. So if we take this point here, for example, starting at 1 times 10 to the 9 cycles to failure, this first tick mark here is 2 times 10 to the 9 cycles to failure, followed by 3, 4, 5, 6, 7, 8, 9, and the last point is 10 times 10 to the 9 cycles to failure, or 1 times 10 to the 10 cycles to failure. So now that we know how to read the scale, let's move on to part A. So part A says determine the fatigue strength at 4 times 10 to the 6 cycles. So let's go where 1 times 10 to the 6 is, followed by 1, 2, 3, and 4. So this point right here is 4 times 10 to the 6 cycles to failure. So what we're going to do is take that all the way up to our data on our SN curve, and then come across. Hopefully you'll do it a little bit straighter than I am, and we can see that our stress amplitude is approximately equal to 95 megapascals. So we can say that for the solution to problem A is our stress amplitude is equal to 95 megapascals. Now let's move on to part B. So part B, we're going to be doing the opposite because it wants us to determine the fatigue life for 120 megapascals. So now let's go to our graph for at 120 megapascals, go into our data or our curve fit, and come all the way down. Now that point right there, we can see is some value times 10 to the 5. So 1, 2, 3, 4, and 5. So this is going to be 5 times 10 to the 5 cycles to failure. So we can say that for fatigue or stress amplitude of 120 megapascals, we're going to get approximate fatigue life, or NF, is equal to 5 times 10 to the 5 cycles to failure. And that's our solution to problem 2. Let's move on to problem 3. So problem 3 says, a cylindrical 2014 T6 aluminum alloy bar is subjected to a compression tension stress test cycling along its axis. The results of this test are shown in the figure below. If the bar is of diameter 12 millimeters, calculate the maximum allowable load in newtons to ensure that fatigue failure does not occur at 1 times 10 to the 7 cycles. You are to assume a safety factor of 3 and that reversed axial tension compression test was used to collect the data and that the S in the figure is stress amplitude. So let's take a minute and determine what the problem is asking us to solve for. So we want to make sure that fatigue failure does not occur for this aluminum alloy specimen at a fatigue life of 1 times 10 to the 7 cycles, given a safety factor of 3. So the first thing we need to do is use our graph and our fatigue life of 1 times 10 to the 7 cycles and find our stress amplitude. So let's do just that. Let's go 10 to the 7 and draw a line all the way up to the top. Now, you'll notice in this figure that there are multiple alloys and materials. So let's figure out which one is the 2014 T6 aluminum. So our 2014 T6 aluminum is right here. So now, with our fatigue life already specified, we can come across and determine our stress amplitude, or sigma A, is approximately equal to, I would say, 180 megapascals. So that's the first step in solving this problem. We can now say that our stress amplitude is equal to 180 megapascals, and all we've done is read that off the graph. So now we can go in and add our safety factor. So for failure not to occur at this given fatigue life, we need to divide our stress amplitude by our safety factor to ensure that we have enough clearance that failure won't occur. So we can say that our stress amplitude is equal to 180 megapascals divided by our safety factor, or 180 megapascals divided by 3, and that's going to yield a value of 60 megapascals. So we can now say that our stress amplitude is equal to 60 megapascals in order for failure not to occur at this given fatigue life. So that's the first thing we need to do in solving this problem. Now, with that, we can calculate our force, because our simple stress equation is equal to force over area. So rearranging, we get our force is equal to our stress amplitude times our area, and that's just going to be equal to our stress amplitude times pi d squared over 4. So we can say our force is equal to 60 megapascals times pi, and our diameter was given as 12 millimeters, so times 10 to the minus 3 squared over 4, and that's going to yield a force value of 6785.84 newtons, or we can say our force is approximately equal to 6,786 newtons. So now that is the force that could be exerted onto this specimen to ensure failure does not occur at a fatigue life of 1 times 10 to the 7 cycles. So before I conclude this problem, I just want to reiterate what I was saying in the previous tutorial. Make sure that you convert all of your units to pascals, meters, and newtons. So this should be 60 times 10 to the 6 pascals. And then that way you'll be able to easily know what your final unit is, and it'll help simplify the problem for you. So now that's the end of problem 3. Problem 4 reads as follows. For a cylindrical S590 alloyed specimen shown below, originally 14.5 millimeters in diameter and 400 millimeters long, what tensile load is necessary to produce a total elongation of 52.7 millimeters after 1,150 hours at 650 degrees C? You are to assume the sum of the instantaneous and primary creep elongations is 4.3 millimeters. So we can very easily determine that this is a creep problem. And every time we're dealing with a creep problem, we want to refer back to this schematic right here, because that's going to set the layout for our solution. So we can see from this schematic that the total creep elongation is equal to the sum of our primary plus our secondary, or our steady state, and our tertiary, which is our instantaneous. And all of that will lead to a point of rupture. So given this schematic, let's write down that fundamental equation, where our total creep elongation is equal to our primary creep elongation plus our secondary creep elongation, or our steady state, plus our tertiary creep elongation, or our otherwise known as our instantaneous. So now with this fundamental equation, we can see that we only have one unknown, which is our steady state. So if we substitute our values and solve for our steady state, and then further provide or do some unit conversions, we can then go read our stress from our steady state creep curve and then determine our force. So that's exactly what we're going to do. So let's plug in the values we have. We know that from the problem that our primary and instantaneous together are equal to 4.3 millimeters. And we know that our total elongation is 52.7. So let's substitute those values. So we can say that 52.7 millimeters is equal to 4.3 millimeters plus our steady state creep elongation. So we can solve for our steady state creep elongation, which is going to be equal to 48.4 millimeters. So that's step 1. Now, with this, we can calculate our strain at our steady state. So our steady state strain is equal to our creep elongation at our steady state divided by our initial length. So that's going to be equal to 48.4 millimeters divided by our initial length, which is 400 millimeters, and that's going to give us a strain at our steady state of 0.121. Now we need to convert our strain at our steady state into our strain rate at our steady state. So we're given the amount of hours that it's being subjected to. So if we divide by the time, we'll get our steady state creep rate. So let's do just that. We can say that our steady state creep rate is equal to our strain at our steady state divided by the time. So that's going to be equal to 0.121 divided by 1,150 hours. And that's going to give us a value of 105 times 10 to the minus 6 inverse hours. So, looking at this value, we can now go to our steady state creep rate graph and calculate our stress. Once we have our stress, we can find our force. But we need to notice that this is kind of in the incorrect unit. The decimal's in the wrong spot. So what we need to do is convert this to our steady state creep rate of 1.0 times 10 to the minus 4 inverse hours. And all I've done was do 1, 2, move the decimal over backwards twice, and then change the power accordingly. So now that is the value we need to read from our creep graph. So we're going to take this value, which is right here, come up, and divide the graph all the way there. Now we need to determine the temperature at which it was conducted at. So 650 degrees C. So find our line that corresponds to 650 degrees C, which is right here, come across, and we can read a value for our stress of 300 megapascals. So now that we have our stress, we can do force over area and calculate our force. So now we can say that our stress is equal to force over area, and then solve for our force is equal to stress times area. So our force is equal to 300 megapascals times pi d squared over 4, where our diameter is 14.5 millimeters. So finally, we're going to get a force value which is equal to 49,539 newtons. So that's going to be our final answer to this problem. However, I want to go over one last thing. Make sure, again, we're changing this to pascals and we're changing this to meters. And that's going to give you a value in newtons and simplify the problem for you. So that's how you proceed in solving a creep problem.